Today I'm going to talk about deep generative models for quantification in function approximation and PD programs. So in scientific machine learning, we mainly focus on three types of tasks. The first one is regression or function approximation programs, and the different for function approximation is deep neural networks. And the second type of task is solving forward or inverse PD programs. One of the popular deep learning model for solving forward or inverse PD programs is PINs, physics informed neural networks. And the third type of task is operator learning programs, in which we use deep neural networks to approximate the solution operator for fast solving PDs. Deep operator networks, DeepNet or FNO. And we will develop approaches to quantify the uncertainties in the predictions of deep neural networks, PINs, and also DeepNet or FNOs. So first of all, I think many talks have already mentioned that deep neural networks for function approximation because we use it because it's a universal approximator. So I will skip this part, and I'll briefly introduce a little bit about the PINs, which is used to solve forward or inverse PD programs. For example, if we have PD here, L is any operator, U is the solution to this equation, and the G is the right hand side. Because neural network is a universal approximator, so we can construct a neural network to approximate the solution to the PDE. And in terms of lower Pytorch, once we construct the neural network, we'll have a symbolic expression for the output of a neural network, which is U here. So with symbolic expression, we can use the chain rule for automatic differentiation in terms of lower Pytorch to get the partial differential derivatives, say the time or space partial derivatives. And if we substitute the derivatives for U into the equation, we can get the symbolic expression for the right hand side R here. So if we try to use this framework to solve a PDE, we can minimize the following loss function. The first one, R, is the residual of the PDE. And the second and third one is the mismatch between a boundary condition and the initial condition. And so we can also use this framework to solve inverse PD programs. So in inverse PD programs, we have some unknown constant or unknown fields or unknown functions in the PD L here, and we will have some observations on the solution, which is used star here. So to solve inverse PD programs, we can minimize the following loss function. The first one is the same as in the forward program, which is the residual of the PDE. And if we have measurements on the initial condition or boundary condition, we can also put it in loss function to minimize the mismatch between prediction of a neural network at boundaries for the initial condition. And the last one is the mismatch between the prediction from a neural network and the measurements for the solution. Lambda here is unknown in the equation. So we can also view it as the trainable variables or hyperparameters to be trained in the neural network and minimize the following loss function to get the optimal values for theta and also lambda. Here theta is the parameters in the neural networks to be trained, and the lambda is the unknown constant in unknown parameters in the PDE. So as we can see, PIN is unified framework for solving forward and inverse PD programs. And also because here we use the chain rule or automatic differentiation to approximate the derivatives in the equation. So we do not have any, we do not use any mesh in the conventional numerical methods. And for the third task is the operator learning programs. We can work with, in this kind of method, they try to construct a neural network to approximate the operator solution. For example, here we have a very, we have a nonlinear differential equation, and unlike in pins, we train a neural network to approximate the solution to the PDU here. We try to construct a neural network to approximate the solution operator. For example, here we try to approximate the solution from U, solution operator from U to from F to U. So this is the architecture of one of the neural network designed for learning operators, DeepNet. It has two sub-neural networks. The first one is branchlet, and the second one is trunklet. The branchlet takes f, the right-hand side of this equation, as the input, which is represented by some discrete values of f. And the input of the trunklet is the x, the coordinates. It can also has the coordinates for time. So the output of deep net is the inner product of the outputs for the branchlet and also trunklet. So in this way, we will use some pair data for f and u to train this neural network. Once the deep net is trained, we can get the prediction, or we can predict the solution to this equation given any new f. So it's very efficient compared to pin. And what we would like to do is to develop some methods to quantify the uncertainties in deep neural networks for function approximation or pins, in solving for the inverse PD problems, and also in deep neural network, deep nets. So why I would like to do this? I will show you a very simple example. For example, here I have an inverse diffusion reaction system. D here is the diffusion coefficient, and K is the reaction rate. We see this one is some kind of reaction. Maybe it's not realistic, but I just make it up. And F is the right-hand side. And so in this case, we assume that we have some measurements, noisy measurements for F and U. And K here is the unknown. We try to use pin to solve this, solve the inverse program. In the first case, I assume that we have some very small noise in the measurements, which are the blue points here. In the first plot, the blue points are for the measurements of U. And in the second plot, the blue points are for F. And as we can see, the red one is the prediction for U and F from pins. If we have very small noise in the measurements, the results are very good for both U and F. And also, the prediction for the unknown parameter in the equation is also very close to the true solution here. But if we increase the noise from 1% to 10% here, so as we can see, the prediction is for U and F doesn't do not agree very well with the reference solution. And also for F, we can see it has the predictions for F are very have many fluctuations, which is what we call overfitting in deep learning. So if we have very large noise in the measurements, it's very easy to get overfitting. And also, so after the model is trained, it doesn't matter if it's a deep neural network or pins or deep net. Once we provide the input, we can always get the prediction. but we do not have idea if the prediction is good or not. So if we break down the total uncertainty in scientific machine learning, we have many sources of uncertainties. The first one is noise in the data, as I just showed. And the second one is mentioned in the first talk of this session. So we have gappy data or incomplete data. And the second type is physical models. So we have a system, and we assume that the physical model is very accurate. Actually, it may be not. We may misspecify the physical model, the physical system. This is also a source of uncertainties in the predictions. And for neural networks, architecture of neural networks, and over-parameterization, and so on. And the last one is posterior inference. I'll go to it later. So the method we developed is try to quantify two types of uncertainties. The first one is the numeric uncertainty, which is caused by the data noise, and it cannot be reduced. And the second type is epistemic uncertainty, which is caused by the noise and limited data. So the key to design uncertainty quantification methods is based on Bayes rule. Say we have the Bayes rule. P theta is the prior distribution for the parameters in the model, and the second one is the likelihood for the data, and this one is the marginal likelihood. And what we would like to get is the posterior. Let's say for a function approximation case, we have a model parameterized by theta here. Say, for example, we can use a very simple polynomial for f. And so we can, for a specific task, we can assign a prior distribution to the parameters in f. And then we'll have a prior distribution. And what we would like to do is to narrow down the prior distribution given data on U to get what we call posterior. And in Bayesian methods, we do not get the. What we would like to get is the so for example, let's put it in this way: the posterior is actually distribution instead of point estimate, as in previous methods like pins or DeepNet. And to present the result, we will have we use the Bayesian model average, which is expressed here. So the second term is actually in the Bayes rule, which is the posterior. So we will present the results in a different way as we said before. And so if we go to the details for the three different tasks, we'll have different posterior expressions for the posterior. I will go to it later, but the idea is the same. We need to use the Bayes rule to get the posterior, and then get the based on the posterior, which we would like to get the Bayesian model average. So one of the most popular methods for uncertainty quantification in deep learning is the Bayesian neural networks. This is a schematic for a Bayesian neural network. As you can see, each of the parameter in BNN is a distribution. It's not a point estimate, like in fully collected neural network and so on. For example, I widely used prior distribution for the parameters is the Gaussian distribution. So let's say we use the Gaussian distribution for as the prior for theta, which is the parameters in the neural networks. And if we have data on U, which we can compute the likelihood, then we can get the posterior. With the posterior distribution, we can then get the posterior samples in the functional space, which is the U here. and that's what we would like to get. We will have, say, a distribution of the predictions instead of a point estimate. If we compute the mean and the standard deviation based on the posterior samples for you, we'll get, say, the red one, the red dashed line is the predicted mean from Bayesian method, Bayesian neural network, and the filled zones are the mean value plus or minus the two standard deviations, which is called the uncertainty bound or uncertainty or confidence interval in Bayesian methods. So as you can see, in this example, we will get the predicted mean and also uncertainty. So it's well known that BNNs with infinite width converge to Gaussian processes. Let's consider a BNN with a single hidden layer. So we can express the output of this neural network as follows. If the distribution for all the parameters in the BNNs are centered at 0 and are identical independent distributions, we can then compute the covariance of the outputs correspond to x and x prime. So I use a new variable sin x here to represent the output of the first hidden layer in BNNs. We can then get the covariance, which is expressed here. So as we can know, it's determined by the standard deviation for the linear layer, the parameters in the linear layer, and also the activation function you used in the BNNs. And for some of the activation functions, you are able to get the covariance analytically. For example, if you use cosine in the cosine function as the activation function in the BNNs, you will get the following color covariance. If you use the RBF activation function, you will get the following covariance or color here. As we can see, both of them are non-stationary. And if you want to get more expressive priors in the function space, you can also use a color compilation operation. For example, addition, multiplication, and so on. Let's see, you use the wrapping. The wrapping, which is in the last one. And for a Bayesian neural network, here you can use what we call a Fourier random feature. Here, you will get a squared exponential curve that we widely used in the Gaussian processes. And the correlation length is determined by the standard deviation for the parameters in the first hidden layer, omega 1 here. So if you use very small standard deviation for the parameters in the first hidden layer, you will get a Gaussian process with a very large correlation length over here. If you increase the standard deviation in the first hidden layer of the omega 1 here, then you will get a smaller correlation length of Gaussian process. In theory, we need to use infinite width BNN to converge to the Gaussian process. But in practice, we cannot make the neural network to infinite. In practice, actually, if you use the width as, say, at least 50 neurons, you can get it actually numerically it's very close to Gaussian distributions. Here, let's say I would like to approximate this function. The target function is on the black line here, and we use BNN with two hidden layers with 50 neurons each layer, and we use tangent as the activation function. And For each parameters in BNNs, we use a Gaussian standard normal distribution as the prior distribution. Then we can get the samples at different locations. For example, here I plot distributions from the samples at x equal to 0.5 and also 1. As we can see, it's actually very close to Gaussian distribution here. So in practice, if we use neural BNN with more than 50 neurons per layer, it's actually very close to Gaussian distribution. We don't need to make it make the width infinite. So the prior and the posterior are two key components in Bayes' rule. So I have already mentioned that twice in BNNs, and the second one is the posterior. For posterior estimation, we actually have lots of methods, say the Bayesian methods, MSMC, HMC, non-linear dynamics, and variational inference, and some methods like deep ensemble, which is based on not BNN, but just fully connected neural network. And we can also explain it in the Bayesian framework for uncertainty quantification. I will not go to the details of each method. I will just show you two typical methods. The first one is let's say it's particle-based methods like MCMC, HMC, or non-linear dynamics. In its methods, we try to sample from the posterior. We try to get the samples for the anomalized posterior. And the second popular method is variational inference. In this method, we first construct a large distribution, which is denoted by Q here, and we can get the samples from Q very easily. Then we try to, let's say we parameterize Q as some kind of distribution, say Gaussian distribution, some other more complicated distribution. We can minimize the Q divergence between Q and the posterior and the true posterior. So after the training, we can use the Q to approximate the posterior, because Q is much easier to sample than true posterior. So we can get the samples from Q to approximate the samples from the true posterior distribution. Widely used assumption is the posterior is a Gaussian distribution. So we will parameterize Q as a Gaussian distribution. But actually, in many of the applications, the posterior is not a Gaussian. So in variational inference or BI, if Q is not expressive enough, the computational error will be very large. Or Q is not so close to the true posterior. Here is an example for using BNN for function approximation. Say this is the our target function, and we assume that we have 32 noise measurements for U, and the noise scale is 0.1 here. The BNN is the same as we showed before, 2 hidden layers with 50 neurons per layer, and we use tanh as activation functions. And theta, the prior for theta is standard normal distribution. The left one is a reference solution, and in the middle we have we use BNN plus HMC. HMC here means we use HMC for posterior estimation for the parameters in BNNs. And the last one is BNN plus mean-field variational inference, which we assume that the posterior in the BNNs are also Gaussian distributions. So as we can see, the predictions will have a predicted mean and uncertainty bound for the predictions from BNN. If we look at the details for the results, so First of all, for the regions that we do not have data, we will have large predicted uncertainty. And if we, for the regions that we have data, uncertainties are very small, which is reasonable, right? And if we compute the error between the predicted mean and the reference solution, the computational error is actually bounded by the predicted uncertainty, which means that if we, for cases or applications that we do not have a reference solution, if we can get a good uncertainty bound, we can just use the uncertainty bound for error estimation. So to make the predictions more reliable. This is the predictions from BNN plus HMC, and we can see it agrees very well with the reference solution. But for the mean field variation invariance, we can get good predictions for both the mean and uncertainty in the middle. But if you look at the predictions at the two ends carefully, we can see the predictions and these two ends are actually very useful. This is because we do not have a very expressive Q or assumption for, because we assume that we use the Q, also assume that Q is a Gaussian distribution to approximate the true posteriori, but actually it's not. So we'll see the predictions and also close to the reference solution. And in this case, we can also see we do not get any fluctuations, as I first showed in the results of the pins. Even we have a very large velocity in this case. That's also an advantage of the Bayesian methods. And in the second row, I increased the noise in the measurements from 10% to 50%. As we can see, we also didn't get the fluctuation or overfitting, as we said before. In addition to function approximation, we can also combine, use the idea of pins to use the automatic differentiation to encode the PDE to BNNs. For example, here, we first use the BNN to approximate the solution to a PDE. And then with the automatic differentiation, we can also encode the PDE to the neural network. F here is the right-hand side of a PDE, and B is the boundary condition. Measurements on U or F and B, we can also get the posteriori, the expression for the posteriori of the parameters in BNNs to quantify the uncertainty in pins. Now here, similar as before, each weight and bias is a distribution. It's not a point estimate. And all the data can be noisy. And in the results, I'll show later, all the measurement errors are assumed to be Gaussian. It doesn't have to be. You can also use some different distributions to describe the measurement error. It's, in the results, I will show, I just assume that the measurement errors is Gaussian. For example, here, I use the same test case as before. It's also an inverse program. So we have some noise measurements for F, U, and K here is unknown constant in the equation. And the blue points are the measurements for U and F. As we can see, at locations that we have data, uncertainty is small. And the locations that we do not have data, the predicted uncertainty is very large. And if we compute the error between the predicted mean and the reference solution, it's also bounded by the predicted uncertainty. And this is a predicted K, the mean value, and plus this is the standard deviation, standard deviation, and this is the reference solution. The computational error between the predicted mean and the the reference solution is also bounded by the predicted uncertainty. So in addition to make the predictions more reliable, we can also use the predicted uncertainty for optimal design, for a better design of experiment. For example, this is also a result from inverse problem. Let's say we have only 3 measurements at the beginning for U, and about 10 measurements for F. We use the BNN or BPin to solve the inverse problem and get a prediction with uncertainties. As we can see, in these locations, we have very nice predicted uncertainty for U. If we would like to decrease the predicted uncertainty or increase the accuracy of the predictions, we will need more data. So if I can provide just one additional data, where should I put it? So a very simple idea is to put the additional data at the locations, at the location where we have largest predicted uncertainty, and use the BPin to train BPin again to get the new predictions based on new data. Here, the blue cross is the new data recommended by the predicted uncertainty, and this is the new data for F. It's also obtained by the predicted uncertainty. As we can see, if we add one data for U and F, the predicted uncertainty decreased a lot, and the predicted mean now agree very well with the reference solution, which is also can be reflected by the predicted uncertainty. We can see in the predicted uncertainty is much smaller in the right compared to the left one. So we can actually perform a loop for the about steps if we want to increase the predicted accuracy better and better. So this is the loop for what we call active learning. We can add one more data at the locations, at the location where we have largest predicted uncertainty, and just do a loop to improve the accuracy. So all the BNNs can provide good uncertainties in function approximation and also in PD problems, but there are still limitations for of BNNs for UQ. First one, in BNNs, the priors are assigned to the parameters in the neural networks. Actually, we care more about the priors in the functional space, which is the output of the neural network. And in BNNs, we can only derive or obtain the kernel analytically with very few activation functions, say remove, RBF, cosine, and some other. And remove some very simple activation functions. For tangent and some sigmoid, we cannot get a kernel for the prior in the functional space analytically. And if we use some different or more complicated distributions as the prior distribution in BNNs, we do not know what the prior will be in the functional space. And the second one is for theory. So because the posteriori estimation is performed in the parameter space of a BNN, so if we have a very small neural BNN, just the 2 hidden layers with 50 neurons per layer, we have more than 2,000 dimensions in the parameter space, which means we have to perform the posteriori the Bayesian inference or posteriori estimation in a very high dimensional space, which is quite insane. So that's why we try to develop some new methods to address these two issues. So in conventional stochastic process or Holonoid expansion or KL expansion is a very widely used method to approximate the stochastic process. Say U is the stochastic process, and mu here is the mean, and alpha and psi I is the eigenvalue and the eigenfunctions from the covariance matrix. Covariance matrix. Theta I are just some random parameters. And if we truncate it at some order, say n, for example, in here, we can use this one, a truncated KL expansion, to approximate the true stochastic process. And the KL expansion is a very effective tool for dimension reduction for expressing stochastic processes. But it's computationally expensive for high-dimensional problems because we have to get the eigenvalues and eigenfunctions for the covariance matrix. So in the KL expansion, the last term is actually represented by the inner product by the eigenvalues and the eigenfunctions. So we try to see if we can use neural networks to make it more general. Say, if we can also use a similar formulation, say the coefficients, inner product between the coefficients and the basis function to express a certain stochastic process represented by data. And here, instead of using the eigenvalues and eigenfunctions of the covariance matrix, we try to approximate the psi here, which are the coefficients for the stochastic process, and the psi I here is the function. And we try to approximate these two terms using deep neural networks. So let's see, we have data for certain stochastic process. We first use the neural network model here, deep learning model here. The first one takes in the representation for the data and outputs the coefficients, which is the psi I in the previous slide. And in the second subnetwork, which takes in the coordinates as input and outputs the basis function. If we have data for a stochastic process or samples for a stochastic process, we can then train this neural network to get the coefficients and also the basis function using the square root between the partition for the neural network and also the data. Once the model is trained, we will have a basis function which is expressive enough to represent all the data in the training set. And we will also have the coefficients for each UI in the training set. But for now, we still cannot generate new samples from the stochastic process because here we only have the coefficients for each UI in the training set. But we have actually have many samples of psi for the coefficients here. So if we can use a neural network to fit the distribution over psi, then we can generate as many samples as we want for a certain for the stochastic process represented by the training data. So there are many ways in deep learning methods to approximate a distribution given samples from it. So we can use GANs, LG-based model, normalizing flow, and also diffusion models, and so on. Here, we just use GANs for its fast inference speed. For example, if we here, so we have two steps. The first step is to get the coefficients and the basis function for the stochastic process. And the second step is to learn the distribution over the coefficients. Yeah, we just use GANs. So the first, this is a generator in the GANs. We use the psi, C are the samples from a simple distribution. Say we can use uniform distribution or normal distribution. Here we just use Gaussian distributions. So C is the samples from Gaussian distributions, and we use the neural network to map it to the coefficients, the distribution to sign. And the discriminator is to measure the dissimilarity between the training data and the output of the generator. So after the training, we can generate, once we sample a new C from the Gaussian distribution, we'll get a new sample for psi. And with the trained basis, we can generate as many samples as you want from the stochastic process. And we'll use it as for the prior in the functional space for uncertainty quantification. This is an example to use the generative model to learn two different stochastic processes. The first one is the Gaussian process with the squared exponential color, and the second one is actually a non-Gaussian stochastic process. So we use the deep generative model to approximate these two stochastic processes given data. This is the comparison between the eigenvalue for the covariance matrix for the predictions from the deep generative model and the reference solution. As we can see, they agree very well. And this is a loss history for the second case. Is a Gaussian process with a very small correlation length. And as we can see, it converges in almost 5,000 iterations, which is very efficient. So the first step, we already have a very flexible model, deep generative model for almost any stochastic process or priors in the functional space. So we actually use a generator to map the samples in a Gaussian distribution to some very complicated unknown distributions. And then we'll have the prior in the functional space. Once we have new observations for a new task, we can then perform the Bayesian inference at latent space for GANs, which is C here. Because the neural network is very expressive, so dimension of C can be quite low. Based on our experience, if we use say 20 to 100 dimensions for C, we can actually approximate very complicated stochastic processes. Once we can get the posterior samples in the latent space of GANs or C, we can then feed it to the generator to get the posterior samples in functional space. Because the dimension of C is quite low here, so we can use many methods for posterior estimation, say HMC and normalizing flow, and so on. So here's a comparison between the generative model and the GANs. The prior, in the deep generative models, we can clearly know the prior in the functional space because it's trained given any training data. But in BNN, we only have a very limited knowledge on the functional priors. For the posterior, C is much lower, has much lower dimensions compared to BNNs. I'll show you some examples for using deep generative models to quantify the uncertainties in the predictions of say function approximation and pins, and also deep nets. So the first one, we just get some assume that we have samples from a Gaussian distribution. Then we can train a GAN to approximate the Gaussian distribution here. And once we have a new task, the blue points are the measurements, Bayesian measurements for U, and we can use we can perform the Bayesian inference in the latent space of GANs to get the predictions with uncertainties, and we compare the results to Gaussian process regression. As we can see in these two cases, the results are very similar. And we can also use some use non-Gaussian processes as our prior. Let's say we have some samples from this function distribution, a times sine omega x. And these are some samples from the true distribution, and this is the samples generated by the generative model. As you can see, they are very similar. And once we have the prior, and let's assume that we in a new task we have some noise measurements here, blue points here, and then we can perform the Bayesian inference for the generative model to get the prediction mean and also uncertainty here. So as you can see, in the locations where we have data, the uncertainty is very small. For locations where we have we do not have data, and predicted uncertainty will be large. And since we have a very informative prior, so and these locations, although we do not have data, but the predicted mean actually is very close to the reference solution. Here I provided a comparison between the Gaussian process with a squared exponential kernel. Even we optimize the prior in the Gaussian process because the prior is not a Gaussian process. So in these regions, it still have not much larger uncertainty compared to the one with a non-Gaussian process in the functional for the functional prior. So we can also use it to solve some. We can also use the deep generative model I just mentioned to quantify the uncertainties in means. For example, here we have a similar inverse problem. We will have some measurements for f and u. We try to infer QR based on the equation and also the unknown and also the noise measurements. Yeah, I also assume that we have some historical data for f and PR, and we can train again to learn the functional prior for u, PR, and also f. In a new task, let's assume that we have some noise measurements for f, u, and we do not use any data for PR. And this is a prediction from a deep generative model for f, u, and also PR. Yeah, because I use a very informative prior, it's not a Gaussian process. So as we can see, for locations where we do not have data, we can still get very relatively accurate predictions and also smaller uncertainties. In addition to function approximation and also pins, we can also use the same deep generative model to quantify the uncertainties in the predictions of DeepNet. In DeepNet, we will use many or a certain number of pair data f and u to train a DeepNet. So if we use the same data to train a GAN, we can then get the prior in the functional space for f. And then if we combine the output of the generator and the input of the DeepNet, we can then, if we have a new task we have some noise measurements for u and f, we can then quantify, we can then perform the Bayesian inference at a latent space in the generative model, and then with pre-trained DeepNet, we can then get the predicted uncertainty for both f and u. For example, here I have a fractional differential equation. R here is the order of the fractional, and here we first train a DeepNet from f and r to the solution of the CPD u here, using data f, r, and u, and then we train a generator to approximate the distribution for f and alpha, which will serve as the prior for f and alpha. In a new task, let's assume that we have some noisy measurements for f and u. or try to predict f and u in the whole computational region, computational domain, and also posteriori on the prediction with uncertainties for alpha. So this is the red dashed line is the predicted mean and the predicted uncertainty for alpha and u, and this is the predicted mean and the uncertainty for alpha, and the reference solution for alpha is here. So as we can see, in all the predictions for all the results, the computational errors between the predicted mean and the reference solution is bounded by the predicted uncertainty for both Fu and alpha. So previously, we just use HMC for Bayesian inference in the latent space. But HMC cannot handle problems with big data. Here, we can use a lot technique for posterior estimation, variational inference. Here, we do not use mean field variational inference, in which we assume that posterior is a Gaussian distribution. We use another generative model, which is normalizing flows, to provide a more expressive expression for the posterior. I will not go to the details, but the advantage in this method is it can perform the mini-batch training to handle problems with big data. I'll just show you one example. Here, it's a function approximation case, and this is the prediction with uncertainties for the full batch training, and this is the results from mini-batch training, in which we use different mini-batch sizes. As we can see, these results actually agree very well. This is the golden rule from HMC. In HMC, we cannot perform mini-batch training, just full batch training. In variational inference with normalizing flow, we can use the mini-batch training to handle big data. Okay, I will skip all the numerical results for AI, for VI, and just show you one example for library for uncertainty quantification using, say, CNN or generative models, as I just showed. So in this library, you can use different uncertainty quantification methods, BNNs or deep generative models, or just conventional fully connected neural networks for uncertainty quantification. Because in some cases, you do not care uncertainty so much. You just want to get the prediction very, very fast. So you can use some simple methods to get the uncertainty, but not so accurate, very, very quickly, very fast. And in some cases, you may need uncertainty to be very accurate, and you can accept low computational speed. So we provide about 10 different UQ methods in this library to quantify the uncertainty in function approximation for the inverse PD problems, and also deep operator learning problems. And this is an example for coding in your UQ. For example, for the function approximation case, the first step is to train load the training data. And the second step is to specify a surrogate model. Here you can use fully connected neural network or BNN GANs, which is the prior in Bayesian framework. And then you need to specify the likelihood, which is also in the Bayes rule. So once you have the prior distribution likelihood, you can construct the posterior. Next step is to get samples or use some tactics to approximate the posterior. And you can use the inference modular to choose different posterior estimation methods. For example, if you use HMC here, just need to specify some parameters in HMC. And then you will get the results below. So in addition to HMC, you can also use some different posterior estimation methods, say variational invariance, and also in the inference material. And this is an example for solving an inverse PD problem. The setup for the setup for solving PD problems is actually the same as in the functional function approximation. What you need to do for the PD problem is to just define PD as an additional function to combine the solution of the PD and also the right hand side and the boundary condition, initial condition, and so on. We just need one additional step for the PD problems. And we have more examples, say function approximation, solving PD or inverse PD problems, and also applied learning problems in GitHub. If you are interested in this part, you can go to GitHub and download the package to play it with yourself. Play with it by yourself. Okay, I will stop here to get any questions. Thanks.
Okay, thanks for the speaker. And any questions and comments from the audience? We have 5 minutes to ask questions. Okay, I have a question, Professor Meng. I want to ask about the training efficiency of GAN with P. Because I know sometimes GAN is not easy to convergence.
Yeah.
So I want to know the CPU time. Yeah.
So our methods, we do not try to approximate very high dimensional distributions, just for the coefficients of the basis function. So it's actually at a order of 100. Based on our experience, it converges in, I think, less than 10,000 iterations. Yeah. Okay. It just takes a few minutes on, say, not so latest GPU.
Okay, thank you. And the next question is about, have you ever tried to combine diffusion model combined with P model?
Well, yeah, but actually you can just replace GANs with diffusion model.
Oh.
It's actually the same. So you can use blue matching diffusion model to replace GAN. Okay. Yeah.
Okay, thank you very much. And any comments or questions from audience? If not, let's thank for the speaker again.
Thank you.
Thank you.